Hello everyone, I'm Max and welcome to our 9th lesson, Polynomials. Before we really start with general formula and behavior of polynomials, we need to know what certain parts of the formula or behavior actually are and how to see them. Where better to do that than on a linear function, aka the simplest polynomial. A linear function is the first degree polynomial, which is represented as a straight line on the graph. But there are only two things here that we are really interested in. The first one is k, also known as the directional coefficient or slope, and the second is n. But we will cover that later on in the video, because it falls under a different subchapter of functions. The formula for slope can be calculated from the graph, or just mathematically from the function. f of x is kx plus n, where n equals 0, or by getting it from the graph. First, let's do it mathematically. We have the formula y equals kx, so we will isolate k by dividing both sides with x. So this is our formula. And now, since slope refers to a change of elevation, crucial word here being a change, we need to adjust the formula a little bit. This is the introduction of another Greek letter delta, which refers to a change of sorts. We will use it a lot more in physics, especially anytime some value is changing, usually on a smaller scale. For instance, formula for velocity would be delta of distance divided by delta of time, where we use delta as a shorter way of saying change of. If we write out delta y, we would get the difference between y2 and y1, which on the example in the top right would be y2 equals 1 from the blue point, and y1 equals 0 from the black point. We would then divide that with delta x, which is x2, that is 1 from the blue point, subtracted by x1, which is 0 from the black point. So, in a way, delta is like an absolute value, but not between a value and a 0, but between two values. And it can also be negative depending on which point you choose first. An example of a negative delta would be if the function is decreasing, so instead of the red line going up as the x increases, the red line would be moving from second quadrant to the fourth one, so down. That can all be predicted from the coefficient. Also, it is important to note that some literatures use different letters for the slope and constants, so it is important to clarify and check for clarifications to be on the same page. I may be using k mostly, sometimes I will use a, and I think in physics and chemistry there are some examples where I will use s, because other letters will be taken. But back to the point at hand, if the slope is negative, the function is decreasing, if it's positive, it's increasing, and if it equals 0, the function is a constant, so the y doesn't change. Now here is another way of writing this, and it's using lowercase d, which is mostly referring to derivatives, which when we cover them, you'll see they're basically the slope on a given point of the function, which mathematically, like off of the graph, is super hard or even impossible to determine, but there's a special formula that we will learn and some tables. I'm just mentioning this here in case I use dx or dy before covering them. After all, delta is the Greek letter d, so technically this is still accurate. Now, let's see what transformations are and what they do. Since simpler polynomials are easier to predict with them, examples like x squared plus 3 and such might be the best case for us to learn it on. First, let's see which transformations even exist and how do they show. Here is our example, x squared plus 3. First of the two transformations is a shift, which is further divided into two shifts, vertical and horizontal. Vertical is when some n value is added to the y, which moves it up or down along the y-axis, while horizontal is when some n is added to the x value. Best way I have found myself understanding this is that I imagine the simplest function I can find, meaning it only involves x's and nothing more. So in this example that would be x squared. I call that function gx, for instance. That gx is another marking for a function, since if you work with multiple, you can use hx, ox, px, rx, and they all refer to some function, usually the one you define it as. Next up, we see where the value is added. Here I have two options that we can get. Either we increase x, or we increase the y, because we remember that we can replace the f of x with y for the graphs. So, either we're adding the 3 to the y, or we're adding it to the x before we run it through the function. Let's solve both examples and see which is right for our specific case. So we take this value of changed x and replace this x with it. let's say this is the value of the new x, and we put it in, and I hope you still remember how to solve the square of a sum, and that is a squared plus 2ab plus b squared. So I plug in the numbers, I calculate, and I get this, which we see is not the same. For the second example, we have x squared, as in x is the only thing we run into the function, and then we add a 3 on top of it, which we actually get f of x. Now, here I have a Desmos example showed. Each of these two results is a shift, but one is a vertical and the other one is horizontal. Here are the two graphs that correspond to the function that I marked them. Blue is being the second one, so the vertical shift, while the red one is being the horizontal shift. As we remember, x squared has its vertex in 0.00, so if the only term is x squared, here when we added something to it, it has moved. So we increase the y. We see that the red parabola has moved to the left and horizontally, which we can see happens because we added a value to the x. Now, why left, which is a negative for x values on the axis, when we added a number that's positive? Well, here we have to think backwards. Let's say that the y value on the graph stays the same for both inputs, the original x and the modified one, which is the one with the added n value to it before putting it in. Here, there's an equation for this that can kind of show you how to visualize this better. The x0 refers to the x on the x-axis before we add and subtract the n, which is done even before we put that value into the function. xi is the x input value, so whatever we did to the original x before putting it into the function. So again, y is equal to the value of running xi into the gx function, which is x squared. xi is obtained by taking the x value on the x-axis and adding 3 to it. So all in all, first we take the value on the x-axis, we add 3 to it, then square it. And the final result is the y value of the x picked on the axis. So if we reverse the process to determine which way it should be moved, by fixing the y value, we would see we need to move the x0 into the negative x direction to compensate for the increment of x before using it in the function. I hope this was all clear, as this is how I understood it, while our teachers just said when you have x plus something, you move it to the left, and when you have y plus something, you move that up. And for negative values is the other way around, which they simplified way too much. Most people didn't understand it, they just memorized it. So a lot of people got this wrong. As for the blue example, increasing the y value after it's been calculated just makes sense to be moved up. I hope this clears out shifts so we can move on to stretches and compressions, or narrowing and widening the graphs. Here is the stretch and compress. Here technically we could say that vertical compress or stretch and then the same for horizontal. But we can think a bit and realize that if a function is more narrow, it just has to be more stretched along the y-axis, as higher y values are reached earlier, but that makes it compressed along the x-axis and vice versa. So stretching along x-axis would make it wider, which makes it compressed along the y-axis, since the same y value is reached later on the x-axis. I will just show you and explain it simpler. It is all determined by the k multiplied with the x, or y. In this case, while yes, it is slightly different based on where k is multiplied, it doesn't change the effect, aka wider or narrower graph. I know this is all confusing, so let me show you the visual comparison of the two graphs compared to just x squared. So the blue parabola is the basic x squared, and we see that when the k value is bigger than 1, as in the green example, where the graph will become more narrow, as it extends along the y-axis, since any result is just 3 times bigger than the default one would be, where k is 1, of course. Okay, so here is a video example that's shown in Desmos. I can change the coefficients, where the first example that I'm showing is when it's multiplied to the y value, so after the x has been squared. The second one will be when it's been multiplied directly to the x before it's been squared. In the second example, we can also see that since k will not be negative due to the even exponent, the graph will not curve downwards. However, it is important to remember that there could still be a minus in front of the bracket itself. As for the shifts, your homework today is to follow my example and make a Desmos setup in which you can change the variable the same way I do, and it will simulate how a graph moves based on where the value is added. So let's get down to the question. What even is a polynomial? To answer that, it is a function written something like this, where we usually use px to show we are working with a polynomial. We can also use q of x, r of x, k of x, but as long as there's a bracket and x next to the letter, we know that it's a type of function that changes as x changes, since we know that this is how you show the independent variable that the function is dependent on. So it is written as the nth term plus n minus first term, all the way down to n equals 0th term, where x to the power of 0 is just 1, meaning that the term is comprised just out of a0. A's are coefficients, each labeled with the position that they belong in the formula at least, because in the real example you just have a number like 2x to the power of 5. An is the leading coefficient, so the one next to the x to the highest power, which makes it the leading term. So the entire thing together, the coefficient and the x raised to the highest power, that is called the leading term. The highest n, which can be found by looking at the exponents of x's, is the degree of polynomial, which, if you remember me saying the first degree polynomial for the linear function, that's because the x is raised to the power of 1. The a0 is a constant term, which is just a move up, down along the y-axis, and does not change its absolute contribution or the value regardless of how x changes. And n is an element of whole numbers, meaning all variable exponents must be either natural numbers or a 0. Also, each term is called a monomial. Damn, this is a hard word. But yes, I think these are the most important words to remember from this, so we can keep on solving math. Now let's check one example. We have a polynomial of 4x to the power of 3 plus x minus 2. We will first check for the degree, so we check for all the x's and their exponents. We see that the highest one is 3, so the degree is also 3. Now let's look at the term that has the highest exponent in it, and that is our leading term. So the third power appears here, so we check this entire term. In our example, that is 4 times x to the power of 3. And the coefficient in that term is 4, which makes it the leading coefficient. For our next example, we have a polynomial of 2x cubed plus 5x to the power of 5 minus 5. So let's look for the highest exponent of the x. Our three exponents that are present are 3, 5, and 0. 0 being part of minus 7, since x to the power of 0 is 1. Meaning the second term, 5x to the power of 5, is the leading term, and the degree of the polynomial is 5. So here we can see that the leading term does not always have to be the first one in the writing. It has to be the one with the highest exponent, because some teachers just try to trick you that way by adding it into the exam by switching up the terms. Next is how we calculate using polynomials. First up are addition and subtraction. That's when we add polynomials together. This is nothing special. We do this just like we did with equations and expressions, where we just had different variables, or even the same variable to the different power. So here we will add and subtract the terms that have the same variables raised to the same power. So we will combine 3x and minus x into one term, while x to the power of 2 will be added to 2x to the power of 2, but they will make their own separate term, which gives us our result. For multiplication, it's literally the same like when we were multiplying different expressions like square of a sum or even cube of a sum or difference, where we multiply each term in one bracket with each term in the other bracket, then add them together like we do in addition and subtraction. So again, nothing new. Next is division, and this one is a little bit trickier, as we have two types of basic division basically. One is for any denominator that is of lower degree than the numerator, and the other is for denominators that are polynomials of the first degree only. First, let's check the general one, which requires a bit more space and lines in your notebook, but once you know it, it becomes very handy and easy to do, while slightly harder to understand how it works or why it even works. So, every division can be rewritten like this. If we divide a by b, we get some whole number, let's call it c, plus some remainder. Like the example underneath the rule, 14, we divide 14 into the biggest number that is divisible by 3, without leaving a remainder. That is 4. Then subtracting it from 14, so 4 times 3 is subtracted from 14, which is 14 minus 12. The remainder is 2. So to write this correctly, we divide the remainder by b. And this is one correct way of writing division. This is also learned before you learned fractions, so that's how your teachers taught you, maybe. So like divide number with another number, you get the result and just write in on the side remainder 2. You didn't have to divide it, but in the written form, it would be 4.67. Now let's rewrite the division rule as we see on the right, and we can rewrite it as the denominator multiplied by some number that would be the result, then adding what the remainder would be. This may be complicated, but it will help us with this division specifically, because we just multiply both sides by b, and you get this formula from the left one. Anyway, enough overcomplicating, let's see how this could even be useful in polynomials. Let's translate this into our lesson. And we get that the polynomial px that we are given is a result of multiplication of qx that is also given, and kx, to which we add the remainder rx. Here are all written as functions, as they can all contain the x variable, but we do have to note that the degree of the remainder is greater than or equal to 0, but strictly lesser than the degree of q of x. And also that the degree of k of x will be equal to the difference between the degree of p of x and q of x. Our goal is to calculate the k of x and r of x, so let's see how to do that. Before we do anything, it's always nice to order polynomials, so they start with the leading term, aka the one with the highest exponent, then proceed so every next exponent on x is lower than the previous ones. After that, let's start with the division. Now I'll cover the steps, and then after that I'll show you how they work in practical use. So first, we would divide the leading term from our p of x with the first term of q of x and write the result on the side. Next up, we take the result, which will always be a single term, and multiply it back with the entire divisor, so the entire q of x. And the new polynomial that we get is written underneath p of x. Next, we subtract that multiplied result from p of x, reducing it ever so slightly. But that does give us the remainder. We can keep dividing that, which is recommended, of course, as that builds up our k of x much more accurately, while making the remainder much smaller. That's like... Actually, I have an example later, so I'm not gonna get off topic too fast. After that, we repeat the first 3 steps on the new reduced polynomial. So we divide the first term with the first term again, note the result, multiply with q of x, which stays the same to get an intermediate, which is reducing the original or already reduced the p of x. We stop this when the remainder's degree is lower than the one of q of x. I hope you could follow along, but if you couldn't, that's alright. I'll solve a few examples and explain it all step by step again. So our p of x is x cubed plus 2x squared plus x plus 3, and we will be dividing it by q of x, that is x plus 1. So let's write this down, that it's easier for us to look over it. I will also slightly reduce the font size on examples that may be a bit longer, so you can already see how complicated it can be. So we write them out like so. We take the first polynomial divided by the second one. Next, we take the first term of the numerator, so p of x, and divide it by the first term of the denominator, the q of x, just like that. The result is noted and saved on the side, so our next step where we multiply is back to the entire q of x. And that way it's also easier, along with the construction of the result. Now, on paper, the most correct way is to keep writing the results here, but I'm just gonna go the long way and easier to read. So, the result is noted and saved on the side, so our next step is where we multiply it back to the entirety of q of x. Then we construct a change. So following the red arrows, I multiply them back and put them under p of x. We see that the x to the power of 3 gets cancelled out, and we're left with x squared plus x plus 3. So we set the division with q of x again, since the degree in x to the power of 2 is greater than x to the power of 1. Now we divide the first 2 terms again. We get x. We multiply that back with x plus 1. We get x squared plus x. We see that both x squared and x get cancelled here, so we're left with only 3. And since 3 has a degree of 0, which is less than 1, we stop here. Now, what exactly is the answer to this division? Technically, you would be writing all of these results in a line here, so this all would be k of x. and this would be the remainder. So I have circled them accordingly. The final remainder with a degree lower than the one of the q of x is r of x. So let me tidy this all up a bit and write the formula and next to the graphs. So p of x is underlined in red, and it also represents the red curve, while q of x is underlined with white, k of x with green, and r of x with blue. Now let's see if we solve this correctly. We could multiply and solve this backwards since we already are smart enough to be capable of that, but let's do this in decimals so we can actually see the visual representation. On the first one, I'm comparing the p of x with this right part without the 3, so q of x multiplied by k of x, so just this part. And on the right image, I added the 3, so I moved it up for the remainder. I hope this was easy to follow along, because the next two examples we have may be a bit more lengthy in calculations. So next I will divide 2x cubed plus 3x squared minus x plus 5 with x squared plus x. I take the fraction of the first terms of each polynomial. I get 2x. I multiply that back to the q of x, and I get 2x cubed plus 2x squared. I subtract that from the original polynomial, and we're left with x squared minus x plus 5 divided by q of x. We repeat the same division step again, multiply back, subtract, and we're left with minus 2x plus 5. And since the degree of this polynomial is less than the one of the q of x, we're done. So our k of x is 2x plus 1, and our remainder is minus 2x plus 5. Now I hope that you can see how this makes sense. If not, that's okay. I only figured it out as I was making the PowerPoint. But yeah, so let's imagine using the formula in the title. We divide a small number that we know will definitely divide the original p of x, like let's say dividing 200 with 10. Our first k could be 2 because we know that 200 is even, so 2 has to be there. So we write it as 200 divided by 10 is 2. Then we multiply 2 to the 10 to see that 10 away. So we're left with 180 because 200 minus 20 is 180. Then we say, you know what? I can do the 2 thing again. So we repeat it again. So we have 2 plus 2, and then we keep repeating it until we eventually reach 0 on the left. So the remainder is 0 because the remainder is less than 10. We can add all of these numbers that we have from partial division. We add them together and we get 10 times 2 because there's 10 separate divisions in which we got the result 2. And I hope this kind of helped you visualize, because I just figured this way, as I said, during making the PowerPoint. So it's like step-by-step division, divide and reduce, Just like breaking down to prime factors. We did the same thing. We divide by one prime factor and then divide by another. Similar, at least. Now, up to the last example, the hardest one so far out of all of my videos until now, which means that if you manage to solve it correctly, you're learning successfully. And if you don't, that's also okay, because we learn best from our mistakes. Our last and hardest example for this division is here. I would encourage you to pause the video and try to solve it on your own, then keep watching to check if you did it correctly, as that is the best way to learn, to either make a mistake and learn how to correct it, or by acknowledging your knowledge by solving it correctly. Anyway, I hope you paused and solved it, but if you didn't, let's get into solving either way. Let's write them down as we did both before. Divide the first two terms and write out the solution. Then we multiply the q of x to the solution and subtract it from the polynomial. So we see that the first term will always cancel out. Now we're left with minus 15x to the power of 4 plus 11x to the power of 3 minus 4x squared plus 3x plus 7. We take the first two terms, divide them, and we're left with minus 15x squared. We multiply them back again. We subtract again. Watch out for the minus signs, because they will be your nightmares. The fourth power cancels out, so we're left with this. We again divide the first two terms, multiply back. We see that the first term again cancels out. The second term becomes a huge mess of numbers. So then we take the first two terms again, get a number, multiply it back, subtract, and we're left with a remainder whose degree is less than the one of q of x. So we're done. Let's circle out the solution. This is our k of x and this is our r of x. So this is the solution. We see that this works even for bigger and more complex examples. It's kind of similar to how you first learn about division, where you don't go into decimals just yet and just write out the remainder that is less than the denominator. After that you get into fractions or decimal points, so you just solve for the decimal points altogether. After that you learn to leave them as a fraction. Now, as I promised, I will show you a quick array of dividing polynomials, where the function in the denominator is of the first degree. That is called Horner's algorithm. It is a faster way of dividing by the first degree polynomials, and also a much easier way to calculate the value of the function at any defined x. It is also possible to calculate zeros, but it is slightly more advanced, and it's based off of some guesswork on several possible options. So I will leave that as a topic that you can check out for yourself if you really want to learn more. But I will solve a few basic examples so you can learn how to use this method on itself. Let's start with theoretical steps along an example. It is important to note that this only works for divisors in a form of x minus c. So x is not multiplied by any number and it is not raised to any exponent. But why does it have to be written as x minus c? We will see that in a second. So here we'll be dividing 2x cubed plus 3x squared plus 5. First we have to write out all the coefficients of the dividend slash numerator, aka the p of x. But the important part is that we write out all the coefficients from the leading term to the constant, which means that if we have a degree of the polynomial that's like 3, we need to have 4 coefficients, so 1 for each exponent from 0 to 3. Here I made a table and I ordered them out like this. So the leading term, then the second one, then this one that is missing because there's no x, we know the constant is 0, and then 5. Now we use the value of c, which is where the minus c from the condition comes in handy. So we take whatever is added or subtracted to or from the x and multiply it by minus 1 and write that in the corner of the table. So x minus 1, we have the minus 1, we multiply it by minus 1, we get 1, and it's copied in the table. Next, we will take the value from up here, so the leading term, and we will carry it down to the first slot in the last row. Then we multiply the dropped coefficient to c, and write it in the second row under the next coefficient. And after that, we add together the two numbers, mind the sign, as one of or both of them can also be negative, and write the sum underneath in the third row. Then we just repeat the rest of the processes for the other coefficients. And when we are done and can't carry over, the last number under the line is the remainder, and all other numbers are k of x. Now we do have to account for which power of x was with which coefficient, but due to the nice order we chose, we know that if we start from the left, the first term is 1 power lower than the original power was, since we're dividing with x to the power of 1, and per division, when you divide the k of x, its degree is always equal to the degree of p of x divided, or sorry, the degree of p of x minus the degree of q of x. So this will all be 1 less. So if the original polynomial was x to the power of 3, x to the power of 2, x to the power of 1, x to the power of 0, we take 1 away as 1 from here, and we're left with x to the power of 2, x to the power of 1, and x to the power of 0. Both of these numbers here are constants because this has to be less than x, because as long as it's equal to the degree, we have to keep dividing. So the last two will always be constants. So let's carry it over to the result, follow the lines, and we get that the k of x and r of x are these two values. So 2x squared plus 5x plus 5, and then the remainder is 10. Now let's do one more example for division, then I will do a couple for y values. Here we will divide x cubed plus 4x squared plus x minus 6 with x plus 2. So let's fill the table first. I fill the top row with coefficients from p of x, then put the c value in the corner, and I remember the original formula is x minus c, meaning that c is minus 2. I drop the first coefficient down, multiply it and move it up, subtract, multiply, right under, subtract again, multiply right under, and add together, we get 0. So the remainder is 0, which means that q of x divides p of x cleanly, or I can say that p of x is a multiple of q of x. So let's write out the solution and remember that the coefficients are bound to the x that is raised to the 1 power less than the corresponding coefficients in the table were. Now that we hopefully understand the basics, let's move on to the evaluation of polynomials, aka figuring out the y value that the polynomial has at a certain x. Here I will use Horner's algorithm to find out what the y value of the graph would be at x equals 4 for a polynomial of 3x cubed minus 5x squared plus 2x plus 7. I have already set the table and filled the coefficients. Now, what value do we even put in the corner here? Well, we put in the x. Because if we think back, we put on the c from the expression x minus c, so the opposite value of the c in the polynomial formula. But if we remember further down, like equations, if we equaled that equation x minus c to 0, the value of x would be the exact opposite of that of minus c used. So carrying over c to the left side would get us the equation of x equals c. So here we apply that rule and we turn it around and get x equals c, meaning we will use the exact value of x given. So 4 is in the corner. Let's proceed as we did with the algorithm before and see where that takes us. So carry the 3, multiply to 12, add to 7, multiply to 28, add to 30, multiply to 120, and carry down to 127. Now here we get a lot of big numbers, but since we are determining the value of the function at x equals 4, the value we would mark as the remainder is the y value on the graph. I'm pretty sure there's another logic you could explain this, as in like intersection between different lines and graphs and everything where you just equal them, but I don't think we're far. I mean, we are way past that point, so I could explain it, but I forgot when making the PowerPoint and right now, so plus it's not that important because this works in a much easier to understand way. But the p of 4 is 127, and if you take your time and look at it in Desmos, by inserting both formulas, so this one and this one, you will get a point at exactly x is 4 and y is 127. For our next example, we have a polynomial x to the power of 4 minus 3x squared plus x minus 5 at x is 2. So let's set a table. We have the 4th degree, so 5 coefficients, where the one next to the x to the power of 3 is equal to 0. So we put 2 in the corner and 1, 0, minus 3, 1, minus 5. Carry down the 1, multiply, add, multiply, add, multiply, add, multiply, add. So 1 is the solution. This graph at x is 2 will have the y value of 1. Now to finish this lesson off, I will show you a typical behavior with polynomials, which is how the terms influence it, of sorts. Basically, this property is super cool and super nice to know. If you go into Desmos and graph random polynomials, you will see that their shapes are wild, curves, bends are seemingly random. But sure, with more knowledge we could learn how to draw them accurately ourselves, but we aren't there just yet. One of the things we can know about any polynomial is their behavior as x increases or distances from 0, and let's see how exactly. I will give you a polynomial and a graph, and then I will calculate what percentage of the y value is represented by each term at that x value. So, this is the polynomial that is graphed here. We can see that while it does look super sharp and weird, there's also some familiarity to the functions we have covered before. It looks like an odd power function, just slightly more bent, and has turns that change the direction, and it's much more steep. But how could one predict the shape? Well, as I mentioned before, the leading term determines the behavior of the function further away from 0. I'll show you the examples for x is 5, x is 10, and x is 100, so you can see just how soon all other terms may become almost irrelevant, but still important if we want to be really precise. And that is already at x to the power of 5. So we have x is 5. We put in 3 times x to the power of 5 is 9,375. 2 times x to the power of 4 is 1250. Then minus 10x is minus 50, and 6 is 6. Then I divide that number with the total sum of them, and I get 88.6% for the first term, 11.8% for the second term, minus 0.47 because it's a negative and it's taking it away, for the third and 0.0567% for the last term. We can see that the 6, while the x is 5, is like so small that it doesn't significantly contribute to the overall value. But let's keep watching. We are at x is 10, so we multiply 3 times x to the power of 5 is 300,000, which corresponds to 93.78% of the y value, which is here. So this down here is the y value, which is the sum of each contribution. I calculated them. So 93.78% for the leading term, 6.25 for the second, minus 0.031 for the third, and 0.00188 for the last. You don't have to know these percentages, but they're just like to show you how hilariously fast this changes. We only increased our x by 5, or doubled it, and it went for the leading term from 88 to 93. Now let's check for x is 100, so 10 times bigger. So the numbers are absolutely crazy. Our leading term reaches 30 billion, while the 10x and 6 are pretty much insignificant. At x is 100, you already have the leading term at 99.34% of the y's value just from the first term, and then like 0.66 from the second, which if you add it together is 100%, slightly more because I've rounded it up. So this doesn't mean anything, this doesn't mean anything, it's mostly just this one. But yeah, this was it for today's lesson. I hope you have learned something new. Here's obviously the mini test. A few news, I have thought about making Patreon, and I realized that due to my current situation, I do not have enough time to make it. But I will be collecting mini tests and making them as I go. Hopefully one day I can make a Patreon and just post them all up there. But yeah, I am live on Tuesdays and Thursdays at 5 PM London time. And I am pushing an affiliate so I can actually get my channel point redeems. I hope to see you all there. And yeah, if you check out my Twitter, I have made a poll if I should make a Discord server, which I do not think I should make a Discord server like a giant social queue avenue, whatever. I just wanted to have it like a place where I can socialize with people and not like a typical YouTuber that has it to, well, I don't know. I will probably make it because so far the results are very favored towards it, but we'll see. But thank you again for tuning in, and I'll see you all on our next quest. Bye!